If you were a university student who lived by their grades and had ambitions to work within the industry, but also enjoyed a good time, and was asked
how you will design a residential shed.
how would you do it? Would you just go out and build it? Or would you study the lectures, break down the structure's design, drink heaps of coffee and spend all your night on your Casio? To succeed at our goal, we first need to analyse the components of the structural design. Spreading the load together, we needed to break down the assignment into phases and work from there. This is our story. This assignment investigates the key elements of a domestic shed with a Skillion design roof. We aim to further develop our understanding of the structural design process and the structural loading path, using relevant Australian standards and manufacturing paperwork to design each component of the shed. In part 1, we'll analyse purlins, girts, as well as wind load determination, whilst also calculating the design loads, ultimate and serviceability limit states. Live load, dead load, wind load will also be solved and used together to calculate the design combinations for the structure. A purlin is a horizontal beam along the length of a roof made from steel or timber. They support the common rafters and are also used to attach the roof sheeting. A girt is a horizontal structure member fixed to the frame wall. Girts provide lateral support to the wall panels, primarily to resist wind loads. They both play an important part in weight distribution for the shed design and thus were designed first. We began by defining the wind load determination by first analysing the criteria that we were given. With the wind region of A and a topographic class of T3, we used the Australian standard to identify the current shielding capacities for our location, current protection and cyclone risks in place, and as such we can identify the serviceability and the ultimate states. For wind classes from C1 to C4, we can use the Australian standard to identify the net pressure coefficient, in which will assist us for our suction and pressure. With the coefficients known, we can identify the free stream dynamic gust pressure, known as QU. After completing this, we can begin to create the purlin design using these specifications. We were given a roofing clad and insulation and can begin to design the purlins. It's important to identify the weight and pressure of the cladding and the insulation on the purlins. We use the equation of mass times gravity for both. When an external wall is being impacted by wind, it's pushed inward and all other surfaces generally have suction on them, pulling that surface outwards. These pressures act directly on the cladding material and are transferred to the structural elements underneath them, creating tension in the purlins, trusses and the design itself. Testings have been conducted to prevent major damages to the roofing and structures. To overcome damages to roofing and structures themselves, we calculate the greatest possible upward and downward pressure to then use the most economical materials possible. We completed this and found the most severe design combinations, as it was important to consider the worst possible scenarios. This is identified as the purlin line load. We selected the purlin design for the ultimate limit state using the BlueScope Steel Limited capacity table using the span of the design and the required strength. One span is commonly recommended for small designs, but due to the length, we used the double lap spans. This concluded the purlin design. In addition to the ultimate state check, a service limit state check is also completed. The aim is to prove that under the action of unfactored loads and whilst applying certain magnitudes of force, the structural behaviour complies and doesn't exceed the CERMAT limit state design criteria values. We use the formulas as found in the Australian standard to solve for this. We next completed the girding design. This process was similar to that of the purlins, using similar wind load values for both the suction and pressure. Identical process was completed for the north-south elevation in which a section was suitable. A service limit state check was also conducted and found both sections to be plausible solutions. And that concluded part 1. In part 2, we will analyse the stability under wind, which will include the roof and wall bracing as well as the rafters and column design. Bracing is used to support the frame of the shed and is incorporated in the roof and walling design. Bracing assists in resisting lateral loads applied to the structure and provides stability to the framework. Rafters are a series of slope structural members that extend from the ridge down to the wall plating. They are designed by engineers to support the roofing deck and assist in spreading all associated loads. The top of the I section beam is under compression, while the lower section is under tension. A column is a compression member that transfers all loads from above to the connected footing pads below. Columns hold the rafters and beams in place and are used to assist the building's ability to resist wind or earthquakes loading additionally. We began by using the net pressure once again as located in the Australian standard and use the same QU equation as per part 1's findings. The intermediate frame and end frame were designed individually to ensure the structure would be sufficient in resisting the implied loads depending on the location in relation to their pressure and suction wind loads. Once completing this, a truss analysis was conducted. As diagonal members resist tension only, all compressive members could be removed from the model created to determine all the required loadings. We use software analysis to assist us in our truss findings. As specified, equal angle sections were used for the diagonal bracing, as these sections are economically efficient and structurally effective. 50 by 50 by 3 equal angle sections were used for the diagonal members, whilst for the compressive struts, we used the basic truss analysis in addition to SkySieve to identify the members and its forces. Using this, we selected 50 by 50 by 4 to carry out the implied loads. To begin the column design, we had to first identify the axial loads and bending moments by considering the connecting points and the moment resisting connection. The column and the beam connection had been deemed as pin connection. The shed is a brace frame structure. Lateral wind loads were not considered in the column design. However, eccentricity was considered in order to design for bending moments. The column design was conducted through the use of dead load and live loads applied to the structure. The dead loads included the weight of the roofing, insulation, ducting, purlin self-weight, and the rafter self-weight. The live load was determined using the Australian standard, as the loads were deemed to be uniformly distributed. Subsequently, due to asserting the relevant loads, the critical, compressive, and tensile loads were deducted. The columns were designed initially for pure compression with buckle closed about the weak axis. Therefore, using the capacity tables, a section was able to be chosen to carry the load. After selecting this, we could address the criteria with the moment capacity and check the members subject to bending. This gave us the conclusion that the section 100 universal column 14.8 was chosen as it was the most economical section whilst being able to support the implied loads. This process was completed for the end columns. We found the tributary area of the central column is far greater than the trib area of the end columns, therefore a larger section would be required in order to carry out the load applied to the shed. However, the smaller section was available and was sufficient for the central columns, therefore the same section was used for both ends. This concluded the column design. The rafter design was conducted to carry the roof loads applied to the shed. The dead load, live load and wind loads were calculated as per the column design. The rafters were determined to be simple support pin connections and the roof load was uniformly distributed. The critical loads were determined in order to proceed onto the designing the members. The central rafts were designed separately as the implied loads differ due to the tributary area differing between the members. This was conducted to ensure economic efficiency was maintained throughout the design. We found the most severe combination and used it to identify the top flange under compression, and by using the given formula we could select the universal beam. As the bottom of the beam is under compression, the maximum unstrung length was 8 meters, therefore the capacity of the selected beam was not adequate to carry the implied load. In order to overcome this, fly bracing was required to be added to the rafter to restrain the bottom flange. A serviceability limit check was completed to identify the actual rafter weight and the possible loads in it which it may come under. For the end rafters, the smaller section was able to be used as the tributary area of the end rafter was far smaller than the tributary area of the central rafter. The end rafter design was completed using identical steps for the central rafters to identify a member.